Alright, so this is just going to be a short recap where we go over what we looked at in the lecture on Monday, just getting some more intuition for divergence and curl, and then looking at some identities. And then I'll make another video for each of the final sections that we need for the course. Alright, so just to kind of put what we're doing in this lecture in context, we spent a lot of time thinking about scalar fields, either in 2 dimensions, so f of x, y, or a 3-dimensional scalar field, which is a function f as a function of x, y, and z. And in those cases, our scalar field either has 2 or 3 partial derivatives, depending on which one it is. And in order to kind of understand how our scalar field changes, or how getting shape information, we wanted to have a look at the derivatives. So we introduced this idea of this thing nabla, or del, which in 2D looks like so, and in 3D looks like so. So this is really a vector. And then for our scalar field, we applied our nabla in order to get the gradient. So in 2D, we got this thing, and in 3D, we got this thing. And we interpret our gradient as saying, if you go in the direction that our gradient tells us, then you are going to increase your function overall as fast as you can. So that gives us a kind of a way of incorporating all the information from these partial derivatives into something useful. Okay, and we spent a lot of time thinking about that, and then we moved on and we started thinking about vector fields. So if we think about a vector field, now remember a vector field has a scalar field for each component of the vector. So if you take all the derivatives, you end up with 9 partial derivatives. So the question becomes, how can we use this information about all these 9 partial derivatives in some useful format, in the same way that we use the partial derivatives to give us information about the scalar field? And as we said on Monday, there are really 2 different ways that we can use these partial derivatives. There isn't a single thing that usefully captures all the information. So these 2 things that we construct with our partial derivatives are the divergence, which looks like this, and the curl. So what you'll notice from this is we're assuming that our vector field is a vector field of 3 dimensions. So we've got an f1 I hat plus f2 j hat plus f3 k hat. And we will see right at the end of this section you can actually define divergence and curl for a 2-dimensional vector field. So we'll have a look at that. What are our divergence and curl? Well, our divergence is defined as the dot product of our nabla with f, and if you work that out, you will end up with something that looks like this. Notice that this is a scalar, so it's just a number. Okay, so our divergence takes in our vector field, dots it with our nabla in this specific order, and we end up with a scalar. So remember that our nabla acts like an operator. So wherever it gets, so for example, we've got, let's have a look, we've got d by dx in the I hat plus d by dy in the j hat plus d by dz in the k hat, and we're dotting that with our f1i plus f2j plus 3k. So what happens? Well, we've got this term dotted this term, so that's going to give us df by dx. I dotted with I is just 1. Then our next term is going to be this term dotted with this term. This is a j here, let's be careful. That gives us df2 by dy. J dot j is just 1. And then we have this final term, df3 by dz, k dot k. Okay, so we end up with a scalar. Our curl, on the other hand, is a cross product. So it's our nabla crossed with our f. So we would expect that we end up with a vector, and we do. And the components you can work out either using your determinant, however you like, finding your curl, but here are the three components. Okay, so divergence gives us a number, our curl gives us a new vector. And if you feel like practicing, you can just check finding the divergence and curl of this vector field, and just checking our divergence here just gives us 4y, so that is just a scalar. Okay, it depends on y, but y is just a number, so depending on where you're looking, for whatever point you're looking at, you will get a divergence of 4 times whatever your y component is, just a number. On the other hand, if we look at our curl over here, we end up with a vector here. So it's clear that there's nothing quite as clear in our interpretation of these as there was for our gradient. So we need to spend a little time looking at what each of these things really is all about. So let's start by having a look at the divergence, and I'm going to suggest that we head over to a very good website that I've found called Math Insight. Highly recommended if you're wanting to get kind of intuition about this. So suppose we've got some vector field. So here we've got one that's kind of emanating out from a point. So the picture that we want to have in our heads when we're thinking about a vector field, we can think about it as indicating the flow, for example, of a fluid. So an incompressible fluid is flowing. So if you looked at this vector field, you'd think, well, okay, it looks like there's a source of fluid right at the center, here, right there in the center, and the fluid is flowing out from there. So how can we think about our divergence? Well, imagine that we've got a small little ball sitting at the center there. Then if you can imagine, there's always going to be fluid flowing out from that ball. So heading back to the notes, in this case, for this vector field, where we've got we're imagining a source that is producing something, a fluid or a field or something like that, we've always, if we think about a small ball around that source, we're always getting a net outflow of fluid, field, whatever it is. And essentially what our divergence captures is the rate of outward flow from a point. So if you look at the divergence at a point, it says, okay, at that point, mostly stuff is flowing out, or it could be that you have, for example, this two-dimensional field here. If you have a look at this, now everything is flowing towards a point. So here, if you were thinking about at that point right at the center there, fluid is not flowing away from it, it's flowing in towards it. So our divergence there would be negative because it's not flowing outwards, it's flowing inwards. So our divergence here is really talking about, if you look at a small little area in your field, is there a net outflow, inflow, or maybe nothing at all? Maybe you've just got something, you've got a vector field that's just flowing straight through the point, whatever goes in goes out, and your divergence is 0. So if we're thinking of our vector field as the velocity field of some fluid, then if we look at a particular region and we see that our divergence is positive, it must mean that the fluid is being produced there, because there's a net production, there's a net amount of stuff leaving. On the other hand, if we look at a particular region and we see that the divergence is negative, then we know that stuff is being annihilated there. And if our divergence is 0, it just means whatever goes in comes out. Okay, so that's a kind of the intuition that you want to have for divergence. It's measuring sources and sinks of whatever your vector field is. Okay, so let's have a look at the curl. And again, it's helpful to go to Math Insight. They have some very nice pictures there. So here's a nice vector field that looks a little different from the one that we've seen before. Let's see if I can make this a bit bigger. So you'll notice here we've got a vector field that is essentially kind of rotating around a point. So here's our x-axis. Oops. z-axis. So if we look, we've got our vector field is kind of creating swirls around the z-axis. Okay, so quite a different looking thing. What does our curl tell us? Well, we can imagine that we've got a little sphere again, and we're fixing it at the origin, but we're allowing it to move according to the velocity field. So we're imagining that our vector field is kind of pushing our little sphere in the direction of whatever the vectors are doing. So if we think about it here, for this particular vector field, you'll see because the vectors are going round in circles like this, they're kind of pushing the little sphere to rotate around the z-axis. So our curl we design in order to give us some measure of this rotation. So if you think back to the example that we had for our divergence over here, the vectors are just all pointing out. They're not going to induce any motion, any circular or rotational motion in the sphere. So we don't have a curl situation in this particular vector field. But in this one over here, we do. The vectors kind of would induce motion in our little sphere. So we want to be able to measure that. How do we do that? Well, it would be tricky. We want a single vector, so we put a vector in on the axis of rotation. And generally speaking, we pick the direction of that vector, because it could either point this direction or that direction. We pick the direction that means that our motion is going to be, if we put our thumb in the direction of the arrow that's going to show the axis of rotation, then we will have anti-clockwise motion. So our right hand rule, thumb of right hand points in axis of rotation, fingers will curl in direction of motion. Okay, so you can try that with this little image over here, and we use, so that gives us the direction of our vector, and we use the magnitude to say how fast it's going. So the length of the arrow corresponds to the speed of rotation. So obviously if you've got a really swirly vector field that's going around a lot, then you'll have a very large amount of curl, but if it's just going kind of slowly, then you have a small curl. Okay. The other thing to think about, looking at this vector field that we've got here, notice here, this one probably doesn't have any divergence, because it looks like at any point that if you look at any little area, nothing's leaving, nothing's coming back of this vector field. It's all kind of constrained around circles. So this probably has no divergence, but it does have a curl. I don't have an example of a vector field that has both, but you can imagine that there would be. Okay, so back to our notes. So we're thinking about a fluid rotating about so this is actually the z-axis, I think. Okay, and we're imagining a little ball that's fixed at the origin but allowed to rotate based on the vector field, and we end up with this. And here's just a summary of what I've said about how we pick the vector to talk about this rotation. We use a right-hand rule. So thumb goes in the direction, let's read it here. So this is fairly arbitrary, that's something to note. We use a right-hand rule to see where the curl of F should point. Curl your fingers of your right hand in that direction the sphere is rotating, and thumb points in the direction of the curl. All right. So we're going to need to link the idea of the curl to circulation. So I just want to come and just do a bit of revision. We talked a little bit about circulation previously, but let's just have a look at an example. So to just have it formally defined, the circulation of a vector field around a closed curve C is given by this. So it is the line integral of our vector field around our closed curve. So it's basically a measure. So if here is our C, here's our curve, and we're looking at our vector field, here's our vector field F, how much of that vector field actually kind of curves around that curve that we've got there. So you might have a look at this picture over here, and you'd see, well, okay, there's a lot of vectors that kind of look like they're roughly in the direction, well, actually in the opposite direction of our curve. So we might have quite a negative circulation because there's a lot of vectors that are kind of in the direction, in the negative direction of our curve. On the other hand, if we look at this curve over here, now we've got a whole bunch of vectors over here that are in the same direction, and more over here. So we've got probably quite a positive circulation. We've got a lot of vectors that are in the same direction as the curve. Okay, let's actually look at the circulation of a velocity field, and we're also going to look at the curl, and we should see that there's a link between the two. Okay, so we've got a velocity field given by this, and we want to firstly calculate the circulation and have a look at how that relates to the curl. So I've just pulled up a picture here of this velocity field, so you can see that it's definitely got a curl going on, so we know that there should be something there. And let's calculate the circulation. So we want the circulation of this field around a circle in the xy plane at the point x0 with radius epsilon. Okay, so we're thinking about calculating this circulation at around some circle centered at x0, y0. It has a radius of epsilon, and it's oriented counterclockwise. Okay, and we know that, going back here, our circulation is the line integral of our vector field around that curve. So we need to do a little bit of work here. The first thing we need to do is we need to parameterize our curve. And probably the easiest parameterization, so this is a C epsilon. And we know how to parameterize a circular curve away from the origin. You can check that for yourself. The parameterization we're going to use is the fairly standard one we've used a bunch of times before. Okay, and this is for okay, so this shouldn't be any surprise. So if we parameterize that, then we can rewrite our v as a function of t by having a look. So remember, this is our x component, that's our y component. So if we rewrite our v, we get v is equal to, minus omega, it's minus omega times y, so we need the y component. And then it's plus, let's have a look back here, omega times x, so we need the x component. Okay, and then the other thing that we're going to need, so we need, if we have a look, so what we're actually going to do here, we're actually thinking, this was the general formula parameterized where we're thinking of arc length as x, s, but we're parameterizing with respect, we're using r, so in this case, because that's what we're using over here. We're using r's, not s's. So we need our dr, and remember dr by dt is going to be minus epsilon sine of t in the I hat plus epsilon cos t in the j hat. So I've just differentiated this thing with respect to t. So if we need a dr, then what we really have is our dr is dr by dt. Okay, so we're just changing the variable, if you like, but we've done this quite a lot before. So plugging this all in, what do we get? In our basic line integral, which looks like this, becomes our integral over dt, because this is the whole point of parametrizing, is we've taken this out of vector land and into the land of a scalar. So we're integrating over t, which goes from 0 to 2 pi. This thing, but dr is actually dr by dt times dt. And here's a nice dot product for us to do. And so let's just add a page. Now we need to do the dot product of our v and our dr. So go from 0 to 2 pi. Bunch of writing out here. Minus omega plus epsilon sine of t I hat plus omega x naught epsilon cos of t in the j hat. What do we need? We needed that. All dotted with dr, so it's a minus e sine t I hat plus epsilon cos t in the j hat. And this whole thing we're integrating over dt. And you can work through that, and you should find that you end up with an integral from 0 to 2 pi of pi epsilon y naught sine t plus x naught cos t Okay, so do your dot product. Make sure that you've gone from having a vector dotted with a vector into a scalar. Follow this through, and you should end up with 2 omega pi epsilon squared. So this is telling us that the amount of swirl around this little circle here is given by this. Okay, at the moment, that's telling us our circulation. So how much our vector field actually maps around that circle is given by this number over here. How does this relate to our curl? Well, let's work out the curl. So our curl, remember, is our nabla crossed with our vector v, which is so you can go and check the formulae. We take the x derivative of the second component of our vector minus the y derivative of the first component, and this whole thing lives in the k direction. And if you work this out, we'll end up with d omega in the k hat direction. Okay, so I've just realized that this over here might look a bit strange because I don't think I told you the two-dimensional version, which looks like this, but it shouldn't come as too much of a surprise, because really what you're doing when you work out the two-dimensional version of the three-dimensional curl, you just put a 0 k component for your vector field, because you're thinking of your vector field as only having x and y components. Put a 0 in, work out the curl that way, and you end up with just a k component. Okay, so we'll talk about that in a moment, but trust me for a moment, it works. So the magnitude of our curl is 2 pi. And if we had a look at our circulation, I mean, it's 2 omega. And if we have a look at our circulation, it's 2 omega times pi epsilon squared. So really what we've got is our curl says what's happening at a particular point, how much rotation we have at that point. If we look at our circulation, it's our curl over the area of the curve that we're doing our circulation over, because this, remember, is really pi r squared, which is an area. So this gives us a link between our curl and the circulation. Our curl is really the circulation per unit area. You don't need to really know this, but we're thinking about it as the circulation density. And a little bit later we're going to see a theorem that really links together this idea of kind of the macroscopic circulation of in a system and the curl, which is the kind of microscopic. And there's a nice theorem that helps us translate between the two. Okay. So just to finish up, what I should have actually put a little bit earlier, we can define our divergence and curl for two-dimensional fields. The divergence shouldn't be too much of a surprise. It's really just thinking of this as the dot product of the two-dimensional nabla instead of the three-dimensional. And our curl, as we said, you could think about it as taking the three-dimensional version. So you take your two-dimensional vector field and kind of extend it into 3 dimensions by doing this. By just giving it 0 in the 3rd dimension, and then you can go straight ahead and work out a curl, and what you'll find out is that you get this. Okay. All right, so those are the intuitions between divergence and curl, intuitions for divergence and curl. As you might expect, we can find lots and lots of identities. So just pulling together everything we've talked about, we've got our gradient, our divergence, and our curl. And something that you will see coming up quite often if you go on with physics is the Laplacian operator, which is basically the dot product of two nablas, and it's a kind of second derivative-ish type of thing. And we call it del squared. It's also thought of as div grad of phi, and here you can see it gives second derivatives. So when you're talking with a scalar field, this Laplacian is really a way of talking about the second derivatives. For a vector field, we also get an equivalent kind of Laplacian of a vector field, which again gives us a way of thinking about the second derivatives. Thing to note, in quite a lot of books, particularly physics textbooks, they use an upward pointing triangle to talk about the Laplacian. So we've got often this. Okay, so in case you see this, in this case, that this thing over here is not meaning a delta or a change in something. It could be talking about the Laplacian. Sorry. So there are many vector differential identities. Initially they might look a little bit hairy, but if you feel like practicing your differentiation, you certainly can. A lot of them come from the product rule. So over here we're taking nabla and applying it to a product of things. So obviously we're going to end up with something that looks suspiciously like a product rule over here. Again, here we're kind of thinking of applying our nabla to some scalar field that's multiplying a vector field, and it shouldn't come as a surprise. Again, we have a kind of product rule thing happening here. Similar thing over here. Again, we've got a kind of product rule, so notice every time I say product rule, we've got two terms where we're applying nabla to the one thing and then applying nabla to the other thing. And you can keep looking through all of these. The key things that we want to think about over here, things to really take note of. If you take the curl of a vector field, so that will give you some vector, and then you take the divergence of that, that's going to be equal to 0. Strange but true, you can check it for yourself. And if you take the gradient of a scalar field, okay, which is going to give you a vector, and then you take the curl of that, that's going to be equal to 0. Strange but true. And in fact, this is so important that we have some terms to talk about these. So two words that we're going to need. A vector field is called solenoidal in a domain if the divergence is equal to 0. So this is a situation kind of like the one that we saw for the curl over here. If you have a look at this vector field here, there's no divergence. There's no vector field kind of moving out from a particular point. It's just doing this. And if you think about a solenoid, that's really a kind of a cylinder, and that's sort of what this term is capturing over here. It's saying we're all about the rotation around a point and we don't have any spreading out from a point. So that's solenoidal. And on the other hand, if our curl is equal to 0, so we don't have any rotational movement, which corresponds to what we were seeing over here when we looked at this vector field. So here we don't have any rotation around any of the points, it's all just spreading out. So this is a situation where our curl is 0, then our vector field is called irrotational. Ir meaning not rotational. And if we go back to our previous notes, if we look at part H, which is this bit over here, this says that every conservative vector field is irrotational. Why? Because if we look at this equation over here, this is the gradient of a scalar field, which is going to give us, this gives a conservative vector field. And remember, we said that a conservative vector field is one that can be expressed as the gradient of a scalar field. So this equation here says that if you're a conservative vector field, then your curl is 0, so you're irrotational. Okay? And if we look at part G, what does part G say? Well, we're now thinking of the curl of a vector field and looking at its divergence, and it says that the curl of any vector field is solenoidal, because remember, solenoidal says that the divergence is equal to 0. So once you've taken the curl, you end up with something that is just rotating. There's no divergence there. And we have a couple of converses if our vector field satisfies certain conditions. So you can have a look at those. Okay, but these are pretty important, particularly when you're heading forward in physics. All right, so this is kind of an introduction to thinking about divergence and curl. We've also introduced we've practiced finding the circulation of a vector field and linked that to the idea of curl. So just practice getting happy with these terms, and then in the next video we're going to extend our ideas and put together a couple of theorems that help us work with vector fields slightly more easily than we've done so far.